This is question 6 from the SACE Stage 2 Physics Course Companion from subtopic 3.3, Structure of the Atom. This is a fairly complicated and long question. Here we have the line emission spectrum of an atom. We have each of these lines are corresponding from the series limit to each of the electron energy levels shown in the diagram. So here we have essentially 4 lines, n equals 1, n equals 2, n equals 3, and the series limit. And so the first one, the 624.7 nanometers, corresponds to this transition. So that's the red line. The series limit down to n equals 2, that's this one here, that's the green line, and the one down to n equals 1 is the blue line. So that's what's going on in the question. There's also a lot of conversions and different formulas that we're going to be using. Rather than show each of the individual calculations and conversions, I might just quickly go through which ones we'll be using. So first, if we're converting joules to electron volts, then we will be dividing by the charge of an electron, and if we're going from electron volts to joules, we need to multiply by the charge of an electron. The other expression that's fairly common in this question is if we're substituting our wave equation into E equals HF. So if we know that C equals F lambda, therefore F equals C on lambda, then our formula over here just becomes HC on lambda. So rather than doing this every single time, because there are a lot of them, I'm going to assume that you can do both of those conversions and that substitution. So with all that out of the way, let's begin the question. So first we need to calculate the energies of the photons that are emitted in electron volts. So first, we've got all the wavelengths here. It's just a matter of substituting them into our formula, this one here, and then converting it to electron volts. So E equals Hc on lambda. H is Planck's constant, so 6.63 times 10 to the power of minus 34 multiplied by the speed of light all over the wavelength 624. So that's a little bit messy. That'll be 624.7 times 10 to the power of minus 9. And if we substitute that into our calculator, we get 3.18 times 10 to the power of minus 19 joules, which equals 1.99 electron volts. Similarly, for the other photons, we have, we'll do the next one, equals Hc on lambda. So 6.63 times 10 to the power of minus 34 multiplied by the speed of light all over 550 nanometers, which if we substitute into our calculator, we get 3.62 times 10 to the power of minus 19 joules, which equals 2.26 electron volts. And finally, the last photon, we have E equals Hc on lambda, so 6.63 times 10 to the power of minus 34 multiplied by the speed of light all over the wavelength, 440 times 10 to the power of minus 9, and in our calculator that ends up being 4.52 times 10 to the power of minus 19 joules, which equals 2.83 electron volts. So there are our three photon values in electron volts. What we need to do now is construct our energy level diagram, which will look almost exactly like this, but with our energies on the left-hand side. So here we'll have 4 lines, n equals 1, n equals 2, n equals 3, and the series limit. So 0, the first one was minus 1.99 electron volts, the second one 2.26 electron volts, and the last one 2.83 electron volts. So there's our energy level diagram. That wasn't so bad. Now in part C we need to show some transitions that correspond to 3 additional photons that would be emitted from the atom if we have this set up here. Now we've already seen the 3 from the series limit, so from infinity to 3, 2 and 1. The other 3 photons we're going to see are from n equals 3 to n equals 2, n equals 2 to n equals 1, and n equals 3 to n equals 1. I'm going to label these A, B, and C. Now, what we need to do is calculate the energy and wavelength of each of these photons, A, B, and C. Now that's not too bad. Our process is the same for all of them, so first let's do A. Our energy will correspond to the energy difference between the 2 atoms. So here, so let's make sure I label this part correctly, so it's a D. This will be 2.26 take 1.99, which equals 0.27 electron volts, which equals 4.32 times 10 to the power of minus 20 joules. We have E equals hc on lambda, therefore lambda equals hc on E. So 6.63 times 10 to the power of minus 34 multiplied by the speed of light divided by the energy that we just calculated, and that gives us a wavelength of 4.6 times 10 to the power of minus 6 meters. Similarly for B, we have E equals 2.83 minus 2.26, which equals 0.57 electron volts, which equals 9.12 times 10 to the power of minus 20 joules, and our wavelength is hc on E. So Planck's constant multiplied by speed of light all over that energy, 9.12 times 10 to the power of minus 20, and that happens to equal 2.18 times 10 to the power of minus 6 meters. Finally, photon C, so we have our energy is equal to 2.83 minus 1.99 equals 0.84 electron volts, which equals 1.34 times 10 to the power of minus 19 joules, and lambda equals hc on E. So Planck's constant multiplied by speed of light all over that energy gives 1.48 times 10 to the power of minus 6 meters. So they are each of the wavelengths of the photons that we don't see in the line emission spectra at the start of the question. Now, we need to explain why these photons are not visible in the line emission spectrum. So 4.6 times 10 to the power of minus 6 meters, 2.18 times 10 to the power of minus 6 meters, and 1.48 times 10 to the power of minus 6 meters. All of these are outside the visible region. So outside the visible region. So they have a very high wavelength, which corresponds to a very low frequency. So all of these are actually in the IR region of the spectrum, the infrared region of the spectrum, not the visible region. That's why we don't see these in the line emission spectrum in the question. And that's it. So that was a fairly long and complicated question. There was a lot going on, a lot of conversions. We took a few shortcuts, so we didn't have to show every single calculation, but it's a fairly complicated question. It's the sort of thing where if you make a small mistake, then it follows through to the rest of the question. So this is a great learning question, not a great assessment question, but certainly worth working through to get a good understanding of how electron energy levels in the atom work, and how the line emission spectra, we don't actually see the whole spectrum, we only see the small sliver, which is just the visible region. There are often, certainly more photons being emitted than what we can see. Anyway, I hope you enjoyed that question. It's the sort of thing that, this helps you with this stuff. So, hope you enjoyed it, and that's it.